Welcome and hello! Welcome to episode 6 of the currently ongoing Devcom Tutorial series programming for Unreal Engine in C++. And today we're going to be diving down the deepest rabbit hole that C and or C++ have to offer for us. Today we're going to be talking pointers. And when last week I said I'm going to be pulling out my awesome paint skills to scribble stuff, to try to explain it a bit more visually, then I meant that. We're going to be doing paint and pointers. And how that fits together, let's see. Yes, episode 6, pointers in coding for Unreal Engine in C++. This will be very interesting, and the very first thing I'm going to be doing is to send greetings to Special Agent UR003, because you are 003. Hi there! A wonderful evening, or whatever it is when you're watching the recording of this on YouTube. I said this, I mentioned this last week and yesterday when we had the dev talk a bit. Today we're going to be diving down a really deep rabbit hole, because today we're going to be trying to wrap our heads about something that even the most seasoned C programmers still stumble over, and it makes them headaches and other pains. And we're going to be talking about these things called pointers. these things, when you can see this, I already started pulling out my super amazing paint skills. It's like when you I wanted this greeny thing here. When you see things like this, the asterisk. I've also mentioned this quite a few times when I was punching code in my keyboard that I wanted to show you when we've worked on the last few things we did, some of the demos, and especially when we made the game of life, because we spawned actors and we got a reference to the actor, which I said, yeah, that's a pointer, yada, because CPU registers and all that stuff. That maybe didn't make too much sense, and today we're gonna at least try to make a bit more sense into this. Episode 6, yes! Episode 6, The Return of the Hellcat. Yes, may the code be with you, and with you as well. Exactly. Episode 6, yeah, oh, right, exactly, because, yes, episode 6 would be the return. You're absolutely, wow. Yes. When we see these little asterisk thingies here, let me get this mouse out of the way. That I circled green. I think you should be able to see it down there. There it is. There. I think it's large enough for you to see it. Now I need to find this mouse. This little asterisk thingy, we've seen it a lot, and I think almost half the time I forgot it, especially. Sometimes we may the code be with you. Exactly. Absolutely. When we were printing into a log, we have this UE log macro that takes a text, and sometimes we want to put some other text. I always forget the asterisk there. So this tells us, yo, that's a pointer, that's not something, that's only something else that tells us where something is. And I will try to also explain this with two analogies, because there's one comparison, one analogy that I have used so far, which for me kind of works. But our intern at work, he came up with a very nice analogy of himself, because we already talked about pointers at work, and he came up with an idea. Isn't it like analogy explanation here? And this one fits the bill rather well as well. So I'm going to be telling you both, and you can decide which analogy, which comparison works better for you. So the one that does work better for you, you just use that one to try to understand what we're actually talking about. So yeah, when we are seeing these asterisks, and to make things even more worse, they can appear behind something else that's written, they can appear in front of it, and total confusion. And also we got this ampersand thingies here that I'm trying to mark now. This one there. And there's a lot of confusion, because let me start with the total confusion, and then we try to clear everything up, because the asterisk is I'm trying to get the actual precise wording, because it can't be more nice, and with nice I mean confusing and sounding almost the same. This is an address, the asterisk, and let me, oh no, I need to use this one. Let me just switch this over so you can see this a bit better. The asterisk here means this is the address of something, and this is kind of something's address. Yeah, it sounds almost the same, but well, I mean, basically they are the same. They are just an address, like I don't know, some road 24 in some town. That's an address. That's where someone lives, and that would be a pointer. If you get a sheet of paper, and there is max minimum living at some street 42 in some town, that's an address. So this sheet of paper with this address on it would be your pointer, because it points you to where Max is living. Both of these do that, but see, and there's already the confusion, because it's even hard to explain when you try to pretend you know what you're doing. Unfortunately, I'm not having the exact wording, because the exact wording is quite neat. Where it says this is the asterisk is an address of something. Yeah, but that's basically it. The asterisk is an address of something, and the ampersand is something's address. Yeah. So, and now that we have pretty much cleared up all clearances, so now we're totally unclear, we can actually start to dive down into what all of this actually is. Also, these things, those little mean thingies, the pointers, they are good and evil at the same time. They're necessary evil, and I will be talking about this in a minute. They are a necessary evil because they are the biggest difference between C and C++ and almost any other language. Most, if not all, I'm trying to think of one. Even Go doesn't really have pointers, I think. It has something that goes along the lines of pointers. It's a bit like pointers, but then again, it's not completely. It's a bit abstracted still. So Go has something that's a bit like pointers, but all the other languages you will encounter in normal daily life, like C# when you're doing Unity, or C# when you're not doing Unity and you're just doing something else, or or Java, or let it be PHP, or let it be stuff like Python and I don't know whatnot. All these things don't really have pointers, at least not for the programmer. Of course, they do have these things internally because objects are still references. They do these languages do handle these things internally. They handle them quite similar, or maybe even actually with pointers. But for the programmer, you never see them. You never get in touch with actual pointers. You always have your variable, and there's always your object in it. And when you access your variable, and you always access it the same, you have no asterisks, no ampersands, and you really don't care because you don't have to, and actually you can't. But you still have only references. This is also why, if you've tried this in I don't know, C# or PHP, this works almost everywhere. At one part of your code, you have an object. You have an object. It's instantiated. You can use this, and then you pass this object to some other part of your code, so it can also work with your object. So it doesn't create a new one, like for a parameter of a function call. You pass the variable where you have your object in. You pass this to a function call, so this function can do stuff with it. And when that function is done with it, and it did something to the object, like changing a value in the object, after the function comes back to you, you also see the new value in your object. Because objects are always passed as a reference. And what exactly this means is exactly what we're going to be talking about today. So internally, all these programming languages, they handle it for you. You don't have to take care of it. You can't even take care of it, even if you would like to. But in C or C++, you have to. You really have to painstakingly, manually, with your own hand, you have to take care of the pointers and something being passed by reference, by value, and all these things. And this is where these special characters come into play, the asterisk and the ampersand. And this is the biggest difference between C and C++ and every other language, because this is something that almost exclusively is a thing of C. And of course, for everything, there's a reason for this, because C is one of the oldest programming languages in the world of computers. C is I've mentioned this a few times in our past few sessions. I've always mentioned, like, the code we are writing in our shiny and colorful IDE with all its nice features and its super sophisticated code, and we have auto-completion, and it's like super nice. But everything we write is one by one, exactly like we've written it. It's seen by the CPU, because the compiler puts our code that we write into actual machine code. The actual bytes that get directly read and executed by the CPU. So we are very, very close to the actual hardware, to our machine. We're not abstracted away like in most high-level languages. Excuse me. In most high-level languages, like C# or Java or PHP or whatnot, you're completely abstracted away. You don't even have a way to know what machine you're running on, because it's all running in an own little space that takes care of everything. And with C, and this is something you always should keep in mind when coding C, we are running directly on the CPU. We are in direct touch with the inner innards of your computer system. This is where we are. This is where our code lives and is executed during runtime. And this comes with a few advantages, but these advantages also come with a few cumbersome things, especially pointers, because with great power comes great responsibility. There's a stray hair hanging somewhere. It's irritating. With great power comes great responsibility. And the power that we have is that we are running so close to the actual system, which means we can do a lot of things. We can do things with quite a good performance. If you write your code good, we have quite a good performance because there's nothing between us. If you write C# or Java or PHP, you always have something between you, and with you I mean your code that's actually being executed, and the actual machine. Because these languages, they have an abstraction layer. They are not really directly executing your code on the CPU. In C#, for example, but this goes for anything else, but it doesn't make sense. I will say from here on now, I will use C# as a representative for any other programming languages, because I don't have to count them up all. I mean, you know what programming languages you're using, which ones you've used, which ones you may be planning to use. So if you're writing a code in something like C#, that is compiled, yes, but it's compiled in something that's called bytecode. It's not actual code that's being run by the CPU, because one of the reasons is if you have a C# script, you can run this on a PC running Windows. You can run this on a PC running Linux. You can run it on a Mac. You can run it on an Android phone. You can run it on an iOS phone. You can run it on a PlayStation 4. You get the idea. It doesn't care. Your code is completely independent of what platform it's running on. Once you've written your code, once the code is compiled in this in-between state that's called bytecode, which is basically just tokenizing everything you've written. So the runtime of the programming language has a bit more of an easier time to actually see what you've done. So your code is kind of like the C compiler does, but not exactly in a proprietary format. Your code is condensed into only tokens and maybe a bit rearranged, like variable declarations are gathered together. So your code already knows where everything is stored and everything. But then there is the runtime of the actual programming language. And this runtime then parses and interprets the bytecode. And based on the bytecode, the runtime of the language calls internal functionality that will then do whatever you've written there as a command. Like, I don't know, a print message. Like you want to print a line on the screen. In C#, if it's plain, I don't know, there's some log output thingy where you can write directly to the console. So this is compiled into bytecode, where maybe, I don't know, depending on how large the tokens are, there's a few bytes that stand in for, okay, the user wants, or the programmer wants to print some text. Then the text is stored somewhere, and then of course there's a reference to which text it is that you want to print. This is the bytecode, and then comes the runtime of the programming language that then interprets this and sees, okay, the user wants text to be printed, and this is the text he wants to be printing. And then the runtime of the programming language calls actual operating system functionality and just passes all the things you told it. Like, this is the text I want to be displayed. It just passes this over to the programming, to the OS level, or sometimes there's own implementations. This depends if it's a function that actually supplied by the OS. So But it kind of sits in the middle and looks at what you want and then does it. So it's more like it's into interpreting this middle mishmash of bytecode and then doing stuff it can do. This also means that you can only do things the programming language actually supports. Makes sense, right? You can't do anything that the programming language doesn't offer you as a functionality with some higher level stuff like, oh, I want super duper encryption stuff, and the programming language doesn't have a implementation for that. Of course, you can write your own implementation with everything the programming language offers you. So let's consider this a level down. With the lowest level commands, and you can't do things the programming language doesn't offer you as a functionality, even though your computer might be able to do this. And this is the huge difference to C or C++, because, as I've said countless times already, including today, when the C compiler compiles your code, it actually compiles code for the CPU. That the CPU, I've said this so many times, I'm feeling stupid saying it again, but I can't stress this enough. It makes bytes that are directly, without anything in between, are seen by the CPU. And the one who then decides what command it is to be executed is the CPU. That little chip on the main board of your computer. That's the one who sees your command and then decides what to do with it. Not some runtime that's sitting in between. There is nothing between you and the CPU. This is, by the way, one of the reasons why I personally like C or C++ so much. Because I like my CPUs. I like talking to them. So, of course, you're limited to things the CPU can do. So you can't tell the CPU glow in the dark. There's no command for this because it just can't do this. But you can do everything the CPU can or everything your computer can, because from the CPU you of course can access all the hardware and all the memory locations. Not completely, because on modern systems there's actually active mechanisms preventing you from just going stray and accessing all the memory and all the hardware addresses. But this is by choice. This is not a technical limitation because the system can't do it. This is something that's imposed by modern operating systems as a security measure. So in theory, you could do that. And this is the huge difference. So there's nothing in between. And that's also because things work a bit differently. Because in higher level languages like C#, if you have a variable and you instantiate a class and you put your object, you get back, you put this into your variable, you just have your variable and have your object in there. You can directly access your object from within that variable. You cannot pass it without thinking about it. You can just pass it to any other place wherever you want. So other places of your code can actually do stuff with it. Because you have this programming, you have the runtime of the programming language in between. And it knows that when you access this variable as value, as contents of this variable, you want this object. So if you access the variable like with similar with if you just have an int variable or a string variable or whatever, so it gives you a number, it gives you the string, or it gives you the object that you put into the variable, because the runtime takes care of this and it knows, okay, when you access my fancy object, that's the variable where you access this very nice thingy that you built there, and then you will get it in return, because the runtime is actually a very, very huge chunk of something that takes care of all these things. And since we're with C, we're directly on the CPU. there is no runtime in between that can handle things for us, because there just isn't. And also thanks for the follows, guys. I hope you enjoy it. If there's any questions, if anything I say doesn't make total sense to you, then please feel free to just ask in the chat. Or again, if you're seeing this later on YouTube, put a comment down in the comments where they belong. And I'll be checking the YouTube videos of this series once or twice a week to see if there's any comments that either need replying to, or that we maybe could just cover right here, live on stream, or not live later on the recording then. So also feel free, up above me, there's this neat little hashtag. You can use this on Twitter if you have any questions in regarding to Unreal Engine or C++, or I don't know, there's something you want to ask. Feel free to use the hashtag above me or the Twitter handles below me. The first one is my personal one. The second one is the one of our studio. You can tweet at both or thrice of all the three things. So no matter if you use the hashtag or one of the Twitter handles, I will see it, and then I will see that I either give you an answer, or maybe we just cover it here and I give you the answer live here on the stream. That just thrown in. So yeah, we are running directly on the CPU. So we can't put huge objects somewhere, since the CPU can't handle this. The CPU, it has registers. And you know what? Let's start using those awesome paint skills. So we got our super duper nice little CPU with lots and lots of pins that connect to your main board and whatnot. And of course there's address lines. Maybe I should let's call this A for address. I'm not good at writing with the mouse, so bear with me, but I tell you, this looks like a 4. This looks more like an A. So let's call this A for address lines, and then of course we have, because the CPU needs to access all your memory, and let's call this D for data lines. So how the CPU usually works, it puts an address on its address lines, which is a position somewhere in all the RAM modules you have in your computer. Even more fancier if they are RGB, because they also have the RGB stuff has to be addressed somewhere. So there's also addresses in play. So the CPU puts an address. Like you have your memory, you have all your gigabytes of memory in your computer, and then they need to be added. Like, I want the first byte, or I want the second byte, I want the 12th byte, or I want the 4,370,988th byte. And which byte you want, but it's not only a byte. Modern CPUs actually read 8 bytes, because they are 64-bit CPUs, so they can read 8 bytes at a time. But the address specifies the very first one, and then it reads the first and the other 7. And those are then put onto the data lines here. So the CPU says, okay, look, this is the first byte of the 8 bytes I wanna access. And then the value of those 8 bytes is then available on these data lines. This is a bit simplified. If you actually look at your main board and you will, if you're able to, you would actually see how the signals go. There's modern computers are a bit more complicated. There's a bit more stuff to it, but we're not doing build your own computer or dissect your main board and see how it works. So this is just a simplified general explanation. So when I come to other stuff, you actually know what I'm saying and why I'm saying this and why things are how they are, because I'm a huge fan of, if you get an answer, if you get something explained, if you get told something is like this, you should always ask why. Never take something for granted. never say, okay, yeah, he said this is like this. Challenge it. Ask why. It's no problem when the person themselves don't know. There's lots of things I don't know. But then you start looking, like on the internet or other people you know who might know. Then ask around. But I'm a huge fan of actually knowing why things, how they are. So that's why we're doing a really, really deep dive down. I told you, we're really going down this rabbit hole, and this is a deep rabbit hole. Alice would be jealous of this, because no Wonderland rabbit hole is as deep as this one. So yeah, the CPU says, okay, look, the first of the 8 bytes I want to have is this one. And then all those 8 bytes are available here on the data line, so the CPU can then see, okay, those are the values that are stored in this particular memory location. So this is neat and fine. So the CPU can look at one memory location at a time. Now, CPUs can do things like add, subtract, multiply, divide, and much, much more. But just, again, this is quite simplified. But the CPU with those data lines can only look at one location in memory at the same time. It's basically when you have a room, and the room has a few windows, and they are quite far apart from each other, and you're standing directly at the wall. You can only look through one window at a time. I can look through this window, and this is neat and nice. And then I can go over to the other window, and I can look out of this one. But while I'm looking out of this window, I can't see what's in front of this window. Yeah, I know this might not be the best example, but it's the one I came up on short notice. So the CPU also needs a way to remember values and as seen. So it can look at one memory location and see there's one value, and then the CPU needs a way to remember this value. So it can then look at another location and then do something with those two values. And this is why CPUs have registers. And again, modern CPUs have registers that are 64 bits in size, or 8 bytes. So what the CPU can do is, the 8 bytes it's seeing here on the data lines, it can put the values that it's seeing into one of its internal registers. It's like you're browsing through Netflix and you're seeing you look at one thumbnail of each series at a time. You're looking at the thumbnail of this series, and you're looking at the thumbnail of this series. And then you find one that's particularly interesting for you. Then you remember it. Like, I don't know, you write the name of the show or the movie on a piece of paper. So that's your register. So the CPU can, whatever it's seeing here on the data lines, it can put into one of its registers. So it kind of remembers what it has seen there. Then it puts a different address on these address lines. So it will see, most likely, unless all the memory is of the same value, this could happen. But usually it's seeing something else. It's seeing a different. It's seeing eight different bytes, because it's looking at a different location in memory. So the values that are stored in this particular memory location are now seen by the CPU on its data lines. And it can put those in another register, and then it can do stuff. It can do all sorts of stuff. The very simple stuff is that the CPU can then, it can also write, of course, something that the CPU has remembered in one of its registers. It can also send it back into the memory. So the CPU can put whatever is in a register back on the data lines. and then on the address lines it puts the location in memory where it would like to put these values, and then there's some mechanism so the CPU can actually either say, look, the address I'm sending out here, either I want to see what is there, or I want to put in there what I'm currently holding in my hand. So see your memory as a stack of drawers. Well, you have I don't know, your shelf and you put drawers in there, and you are the CPU. And all you have is a little notebook. And with notebook, I actually mean the paper thingy, not computer notebook, but a little a paper. You just have a few papers where you can write stuff onto it. So what you can do is you can say, okay, this particular drawer is of interest to me, and then you can open it, and you can either take out the piece of paper that's in there. This is reading from this memory location, and then you see what's written on there. Or if you already have a piece of paper in your hand, you can say, nah, I don't care what's in there. I want to put this in there. And then you put your piece of paper on your drawer and then you close it again. This is basically what the CPU does. Your memory is a huge shelf of drawers, and the CPU opens them and either takes a piece of paper out of it and looks what's written on it, or it's putting a piece of paper in it when it wants to say something. And when you remember, when you have a second piece of paper, like you take the piece of paper out of the drawer, you look at it, and then you have a piece of paper on your table, and you write the same value that's on the piece of paper you're currently holding, because you picked it out of the drawer. You write this on the piece of paper on your desk, and then you put the piece of paper back into the drawer and close it. You still have the value on your piece of paper on your desk, and this is the register of the CPU. This is basically what the CPU does in these cases. And this is all it can do. And this is the reason why we can't store objects. And because now comes the reason why I'm going into so much detail with this. This is the reason why we can't have complete and full objects in a variable, because since our code is running directly on the CPU, like I said before, with higher level languages where you are limited to what kind of functionality the language itself offers you, like if you have an imaginary language and this language does have no commands for a loop. It doesn't have a for command. It doesn't have a while command. You can't do loops. Hey, Nightbird Hi there. Perfect timing. We are just sliding down the rabbit hole. I'm fine. I'm currently throwing around with analogies and comparisons to make things hopefully a bit more understandable. Jesus Christ, this hair is irritating today. So this might be better now. Imagine an imaginary programming language that's high level, like C# or Java or PHP, but this language does not offer any commands where you can do a loop with. It doesn't have any while commands. It doesn't have for command. It has nothing of the sorts, which means you can't do loops, because the programming language, the runtime of the programming language doesn't offer any functionality that you could use to make loops. Does it have jumps? For the sake of this imaginary for the sake of this example, no. It also doesn't have jumps. Because with ifs and jumps you can actually do loops. I see where you're heading there. But no, it also doesn't have jumps. So because the runtime of the program language doesn't offer this, you can't use this. And it's the very same, but different. It's the same but different when we are running directly on the CPU and we have our C code that's compiled and it's directly executed by the CPU. Because as I've just said, basically all the CPU can do is look at memory locations and remember what it's seen at this memory location in its internal registers. But its internal registers have a size of 64 bits, and that's it. You have 64 bits in these internal registers. This might not be 64, but just imagine this is 64 bits here. So that's all you can put in there. And this is the actual reason. This is the technical reason why I've said so many times before in the previous sessions, we can't have complete objects in our variables. We only have references, we only have pointers where in memory our objects are located, because objects are usually rather large. Even the simplest object, even an empty class, you have an empty class that basically does nothing besides existing, is already bigger than 8 bytes, 64 bits. So there's no way we can store a whole object in the internal I remember things. I'm not saying memory intentionally, because it's not memory as what you would imagine when I say memory. Because the CPU can only remember 64-bit large things, and our objects are way more bigger. It's for another example, it's like you're moving, and you want to take all this stuff with you, all your tables and all your chairs and all your computer stuff. You want to take this with you, but you can't just take it all and take it with you. You have your huge car or transporter or whatever, not Star Trek beaming transporter, but like, the huge 3.5 tons or 7 tons things, and you put your stuff in there. So the car, the transporter, is your memory. This is where all your stuff is. And you remember, because that you can do, that you can handle. You remember where the car is. And this is all the CPU can do. I know this is not the most perfect example, but it's the one I came up with on the fly. So bear with me. But I think it gets the point. I think it gets the point over. Slow down and try again. And this is the reason why we can't put objects into the CPU, because everything we put into a variable has to fit into the registers of the CPU. Because when we are using variables, or especially when we are calling a function and we're passing parameters to the other function that we're calling, all these things are stored at one point in a register of the CPU. So if we have an integer variable, there's a 13 in there, and we want to add 37 onto it, the CPU has to take the contents of the variable that is stored somewhere in memory. It has to remember this in one of its registers, so it can then look at the other value that's stored somewhere in memory, which is the 37, to then be able to add these things together. So everything that we put into our variables has to fit into a CPU register, which is by design on modern CPUs 64 bits in size. So since objects are larger and our variables only can hold things that fit into a CPU register, we can't put our objects into our variables directly. So what do we do? Because we're doing it. So how do we get around this? We do have our huge objects. And if you look at objects that are supplied, the objects we've written in the past few sessions are tiny. They are really, really tiny. They don't do a whole lot. But if you look at objects, like look at a pawn object that Unreal Engine brings with it, this thing is huge. There's so much code in there. There's so many values in there stored there. There's so much going on. How do we do it that we still can use these things, even though we basically have no way of actually handling them because they don't fit in the CPU register? And this is where these little pointers come into play. Because instead of handling the whole object, the object is somewhere in all the gigabytes your computer has. There's enough space for so many objects. It's fun. You can put so many objects in your memory. It's great, and they all fit. But they are somewhere. They are like in the first portion of the second half of the 3rd gigabyte. There is my object. And this is a pointer. The pointer is the address in memory where the object is. And this, the address, so that what usually is given out by the CPU on the address lines, that is the thing we are putting into the register of the CPU when we want to access it, or in our variable. So we are putting into our variable, and therefore eventually into the CPU register, the address the CPU will put onto the address lines. So all your gigabytes of memory know what values and what location for the object you want to access. And then it accesses it sequentially bit by bit. So, or byte by byte, actually. So, let's open up another paint session. And now I have to do some counting. So I think before drawing my lines, I will try. Again, I'm not really good writing with my mouse. So this might look like really bad handwriting, which I do have, but this might look even worse. So 2, 3, 4, 5, look, you can count, 6, 7, 8, 9, A, B, C, D, E, and an F. Because after all these numbers, you have to end it with respect. This is why we stop at the F. This is respectable enough. So same thing here. 1, 2, 3, 4. But this is okay if we just do this up to the 6. Now let's draw some. Maybe I know Paint has line drawing function, so I can draw lines, but this looks a bit more like I have no idea what I'm doing. So when I actually do say something that sounds meaningful, people still get the oh wow effect. This is all on purpose. Okay, and 2 more. Let's finish this up properly like so. And then we got these. Maybe I should have used the line drawing tool. I don't know. But now I'm so far with this. And you're wondering, what the heck is he doing there? Why is he doing that? And why is he counting up to all the respect? There's a very good reason, because this is our memory. This is our RAM. This is a very, very much scaled down and simplified version of all the gigabytes of memory your computer has. So, and this is why I went with the F. I think most of you are familiar with hexadecimal numbers, so you know why there's an F here, and all the other letters, because this obviously is in hexadecimal, because the human readable representation of all the things going on in the data and the address lines is hexadecimal because it fits so nicely with all those 4 bits, 8 bits, 64 bits. We can realize because we can cover all 4 bits. With these 0 to F, we can cover all the 4 bits of 4 address lines we have. And since we have another one here, we can even cover 4 more bits. So 2 times 4 is 8, and all we know, 8 bits are a byte, right? But I don't have to tell you this, because you know this. So this is our memory. So this here is memory location 0, 0. 0 because 2 zeros, this one and then this one. Which one? Yeah, I think this is the first one. We also say this one first and then this one last. So this would be address at address 0, 0, while this would be address 0F. Like, see, this is the 0, this is the F, and in hexadecimal, after 0F, you have 1 0, which lines perfectly up with my neat little grid I've drawn here. Because if we wrap around, if we go from here right back to here, we have address 1 0. So this address would be 6 7. So this little grid is supposed to represent our memory. And for all of those who now thinking, is he drawing paint the whole night? No, of course not. We'll be doing some code examples. We will actually be playing around with pointers in code. I promise you that. We will declare variables. We will look at its contents. We will look at the locations where in memory they are. We will do all of these things. But we're not there yet because we are still climbing down the rabbit hole. We are not even near the bottom. And to get to the bottom of it, maybe this is where the phrase comes from, getting to the bottom of something. I want first to use this a bit to actually explain a bit more and actually visually the things I mean. So this is our memory. And now let's assume, you know what? Let me open another one and let me put them like side by side or something. Let's assume we have a program. Oh, I covered my, this is bad because now it covers my chat. So let me shrink this down a bit because chat must not be covered. Chat must always be visible because chat is important, which is you guys. Because without you, all of this would be kind of pointless, right? So let's suppose we have a program, and in this program we have some function. Maybe does this work better with a graphics tablet? I don't have a graphics tablet, you know, like these Wacom things. I don't have them. Maybe that works better. Then we got our curly bracket open, and eventually somewhere down here we got our curly bracket down, closed. So this is our function, and let me can I mark this? Let me mark this in red. This is our function because all the code, and let me just represent the code with some lines that look like there's something written, because it for this explanation it really doesn't matter what kind of code this is. So this function has code. This function, of course, is part of a class that's instantiated, yada 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 yada. So this class has code, and this code has to be somewhere. The code has to be somewhere in memory, so the CPU, when this is compiled, because of course I'm writing the C, or I'm symbolizing the C code here, but of course I'm talking about the final compiled code that the CPU sees. So this code has to be somewhere in memory for the CPU to be able to see it, to take byte after byte, and then to determine what to do with it. Because, this combination of bytes means I should remember this value. This combination of bytes means I should remember this value. So the CPU has put two values into its internal registers. And then there's another combination of bytes. And this means that the other two numbers you just remembered, please add them. And then the CPU does this, and it remembers in another CPU register, it remembers the result. And then comes a byte combination that says, here's the location in memory, please store your remembered result that I do not know about yet, because please, dear CPU, let me know it. Please put the result of this addition at this location in memory. So this is basically how this works. This is assembly language. So there's your code. And we have, no, first let's, the code has to be somewhere. And let's say it's here. No, red, need to use the red one here as well. So let's say, and again, this is only a symbolized version. So the code might actually be way more, might be a bit more larger. So those red fields, those red squares I'm painting here. This is the memory taken up by our function. This is why I marked this in red, because this is the whole code of this function. This is where somewhere in memory the code that we've written for this function is actually stored. So it begins at address 27 and ends at address 2C. You know, because this first square is first comes the 2 and then comes the 7. So this is address 27. So when the CPU is eventually told, when we call this, when this function is called from some other part of the code, the CPU is told, look at address 27, there's something I want you to execute, and then it starts looking, okay, what does this tell me to do? What does this tell me? Yada 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 yada. So now, and I need to pick a color is actually well visible. Let's try this one. And now we have a variable defined. Let's go with a simple integer variable, and we call this x. So this has to live somewhere in memory as well, because we're putting stuff into this variable, and it has to be stored somewhere in memory. So when you turn off the computer, your computer can't forget it, so it has something to forget. And the compiler takes care. When the compiler looks at your code that you've written, and the compiler sees, okay, look, he wants to have an integer variable, and he wants to call this x. The compiler takes care that you have a known location in memory where the value of this is stored. And let's say it's this one. It's this little square here, right in front of our function, because but this is not really important for today. And I'm not sure if you ever have the need to actually know this, but usually the variables you define in the functions like this, they are put on something called the stack, and the stack of each function usually resides in directly in front of the function. With C++, it's a bit more complicated, and with a bit more complicated, I actually mean it's a lot more complicated. So it doesn't quite work like this there, but in plain C, it actually does work like this. In plain C, when we're not doing C++, when we're doing plain C, plain ANSI C, if we define a variable like this, it's going to be put on the stack, and the stack is a memory location immediately in front of the memory location where your actual code is, sized just to fit everything, just to fit all the variables we have declared. So if at some place in in our code, we now say we want to assign a value to x, like, I don't know, I want to write a 4 into x. Then can I use a color that I can write onto this and you can actually see? Let's try. So I want to put a 4 into my x, which is something we're doing rather often in the code we have a variable, we assign a value to it. Then the compiler knows, the compiler made sure it has reserved some space for your variable you called x. And the mouse is barely seeable. I hope you can follow me. It's here is this purplish blue square. This is where the compiler said, okay, whenever the programmer wants to access his variable he called x, I will look at this memory location and do stuff with it. So if we then say, okay, now we want to put something into our variable and we want to put a 4 into it, the compiler knows, okay, wait, this square is the one I reserved for you. This is the one that I cleared up for you, so you can use it as variable x. And then we're actually gonna be putting our 4 into there. I hope this is visible. Yeah, I think this is okay. This should be okay. So now we got our 4 there. And we didn't care about this whole memory thing. Everything I just said, we didn't really care about this. We just said, come on, I want to have x and I want stuff something into x. And eventually later in the code, when I am accessing x again, like I'm doing some super intense mathematic thing, and I need the value of x for it. In the code we just write the x into. So the compiler again remembers, wait, for the x I reserved you this little square, and now you want to use your x. So let me just check. Okay, there's a 4 in there. Okay, and then it puts the 4 because it's taken the 4 out of this little square. Even I can't see my mouse. It's taking the 4 out of this little square and placing it into our super sophisticated mathematical thingy that we're then using to do super sophisticated math with, so we get the total right result. This is all things the compiler handles for us. We don't have to care about this. We just say, I want this variable called this, and then I'm going to access it. And this is all stuff that happens under the hood, and the compiler takes complete care for us. So now we finally get to the pointer stuff. Because this little x, it has to be somewhere. And it has to have a location in memory. In this example, it's on address 26, because here's the 2, and here this is barely readable. Let's take this color. So here's the 6, and here's the 2. So it's on address 26. This is where our 4 is. So now I can, and I'm going to be taking the same number for this, I can declare a pointer variable. And this is the first time we're going to be using this asterisk thing, because we've used this many times. Do I have some of, like the code we did yesterday? I think at least here. No, also, yeah, well, okay. Do we have some better ones? Do we have some code that we've actually written ourselves? Yeah, here, look. Remember at the very beginning, like, I don't know, the first or second evening, we created a little C++ pawn. Is this the complete one? I don't know. We created the scene components in Unreal. We created the scene components, and we wanted to store them somewhere. So we had our static mesh component, right? Because we had a static mesh that we wanted to remember. We created an object, an static mesh object, and we wanted to save this somewhere. So here you can see this is the type of our variable, and this is the name of our variable. Just like you know, nothing new there. But notice the asterisk here. Because the asterisk means the variable is not really, there is not this thingy in there. It could be int. This could also be an integer, like in the example we're currently doing. But this is not, the contents of the actual variable are not the thing of this type, but a pointer, i.e. an address in memory where you can find something of this. It works way better with an integer. So let's continue there. But this is where we actually used it, and we used it many more times. And last time when we did the game of life implementation, we also used a lot of pointers because we spawned objects and we spawned actors, and we got a reference to the actor object back. We wanted to save this, and this was also a actor asterisk. So if I do this now, if also here I say, okay, I have int asterisk. Let's make one more so it's clear it's an asterisk and not a misdrawn X or something. And we call this, let's call this Y. Well, because why not? So this means exactly what I just said, but with an int, it's way more easy. X is actually an integer. So when we access X, when we access what is stored in the variable we called X, this is of type integer. When we access Y, we are not getting an integer, but we're getting the address in memory, or we're storing the address in memory, or to put it completely right, this variable stores the address in memory where an integer value is stored. So X, we actually have an integer value. We put a 4 in, and this is an integer value. In int asterisk, which is a pointer to an integer, we have the memory address of an integer value where it's in memory. So if we would just here, if we would print out X, we get 4. If we print out Y, we actually, because we haven't put anything in there yet, but let's pretend they look at the same thing. Shortly I will show you how to get the address of maybe X to put it into Y, because this is then the ampersand sign. So yeah, let's for the moment let's just say, for the example, they point to the very same thing. So if we can actually do that, but yeah, we don't. Now let's do something. Let's do it a bit different. Let's put Y. Let's write something into Y, and let's put a 32 in there. So this is, consider this as pseudocode. This is not actually something you could write in directly in C like this, because 32 is an integer. You can't, and you know, C is very, very strict on its typing. You can't put something of the type something into something of the type something else. So this won't work, because 32 is actually an integer, and you can't put an integer into a variable that's only the address of an integer, so you'd have to cast this. But we're going to be doing this. This is actually all stuff we're going to be doing. So please consider this as pseudocode for now, just for explanation's sake. So we put, where's my mouse? Here's my mouse. We put 32 into y. Y again has to be saved somewhere, so maybe actually make y green. Actually make this green, because also y has to be saved somewhere. And the compiler reserved us, oops, I need to pick the green here as well. The compiler reserved us this little square here. This little square. The compiler said, okay, this is the memory square where I will store whatever you put into y. Because even y is only a pointer to a value and not a value itself, the address of the value has to be stored somewhere as well. And also let me do something else quickly, because let me put a 1, a 2, a 3, a 4, and a 5, and a 0 in here. Just for, because why not? Because I like having my memory filled with things. So we're putting 32 into y, which means that the compiler will happily say, okay, wrong color. Will happily say, okay, this is where I'll be putting your 32 into. So, okay. Yeah, that's cool. And now you're going to be thinking, okay, but what? This is exactly the same like the X thing. Just you pretend it's more complicated. Again, this is pseudocode. It will become a bit more clear when we actually start doing actual code examples with this. But before I do this, I want to give you at least a chance to understand what's going on under the hood. Because now we can say, okay, I want to access what's at the address of y. So let's say we do a print x here. This results in 4. And then we do a print. This is horrible writing. If we would do a print of y, we actually would get a 32. But we can say, okay, wait, I don't want the address. I want what's stored at the address. So, and this is where the confusion really starts. We can put an asterisk in front of the y. Up here, it's actually in front of the y as well. If you look at it, it's actually in front of the y as well. And where you put it actually doesn't matter. So the white space between this doesn't matter. You can say int asterisk space y. You can say int space asterisk y. So this actually is in front of the y as well, because this is the syntax for this is a pointer. This is not a value in itself. This is just the address of a value. And when we want to access what's in there, we also put the little asterisk in front of it. And then magic happens, because the result of this will not be 32. The result of this will be 3. Why does this, here, there you can see my mouse pointer. Why does this give me a 3? Because we put 32 into y. And since y is the address of an integer value, and if we look at the address 32, which is, here's the 3, there's the 3, and here's the 2. So it gives us the contents of the memory location 3, 2. And this is why I put stuff down there. Sneaky me. And the contents of memory location 3, 2 is 3. And you might even be a bit more confused than before, because you're saying, wait, this is basically the same. You put 32 in here. If you print it out to get 32, can I just put something in X and then put an asterisk in front of the X to access whatever is at the address of what I've put into X? Yeah, and this kind of works, but you have to remember that C is very, very strict on its types. Again, this is only pseudocode. When we do the actual code, you will see, or I will try to demonstrate that things don't really just work like that. There's a bit more to it. Because if you just put an asterisk in front of the X, the compiler will know that X isn't an address. X is a value. So the compiler will tell you, I can't do we put the 4 into X, and if we would put let's have, I don't know, black. Let's have a black. Let's have a 13 in here, a 37 in there, and maybe a 42 in there. And if you now put an asterisk in front of the X, you might expect to get a 37. Because at memory location 0, 4, so we only put a 4 into it, so we put a leading 0. So on memory location 0, 4, we have 37 in there. This doesn't work because the compiler knows that X isn't an address, so it will tell you, you can't use this as an address just because it isn't one. It's this strict type safety. And this is why we had to define our Y as an actual address or something, because then we can say, then we can actually get both things. Then we can say, okay, give me the address and give me the contents, because since this is an address, the compiler knows how to handle these things. However, you can do this. You can put a 4 into X and then access the memory location that of the 4 you put just in there. You just have to cast it. For those of you who have already worked with C, or this also exists in higher level languages like C#, Java, and all those. You can cast a variable or a value to a different type. So you can say, dear compiler, here I have a value that's of type int, but I want to be it a float. And then you can cast this to a float, which is in classic C, it's just bracket open, new type, bracket close. C++, plain C++ in not Unreal Engine, has special casting inbuilt language construct. Casting, it's not really functions. It has casting things you can use and you have to call to actually do the casting. But we will be doing this. We will actually be doing this. We'll be casting around pointers to values and values to pointers, and eventually maybe our program will crash and then we will look why it crashed and all the yada yada. We'll be doing all of this. I promise you. So just stick with me for this very, very basic, very, very low level explanation. I promise you it'll be worth it. Because once we actually go into our IDE and we start writing C++ code to actually do all these things, we will be doing this. We will be casting around. So we will be putting into X and we will make it into a pointer and we'll try to access it. And I promise you it'll crash because access violation. Because the operating system will most likely tell me, dude, what are you doing? No. Which is a security measure of modern computer systems. On older computer systems, you can actually do this. On older computer systems, You can do, oh, this is science and technology, okay. This is an arts channel. Yes, yes, I told you. I will be pulling out my finest paint skills. And if I say I'll do this, I will do this. On older systems, you can actually do this. You can put a random number into your variable, and then you can try to access the memory location that what you just put in there. On older systems, this actually works perfectly fine. Just on modern systems, it doesn't, which is intentionally and an active mechanism for security reasons. Because if you would be able to do this, you could access memory locations of other programs. And then you could manipulate the memory contents of other programs. And then you might get things like cheat engine or something. So yeah, this is basically how these things work. When you got an integer variable, you just don't care where it is. But when you have a pointer, you actually care about the memory location, the memory address. So let's say we have our sum function here. And let's say we have another piece of our code. And just for the sake of demonstration, again, this is all pseudocode. This is nothing you can actually type into your C compiler. So it works on modern systems too. If you use cheat engine, you can manipulate the number of game. Yeah, but cheat engine, there's more to it. There's more to it. Cheat engine has to cheat a lot to actually be able to access memory locations of other processes. I think it starts with you have to run it as administrator. You have to run it with administrator rights. And then it has to convince the operating system to actually let it access these things. So yes, cheat engine actually does do this even on modern computer systems. But there's a lot of work involved with actually making this possible. It's not done with just putting a memory address into a pointer and then just accessing it. This doesn't work. It doesn't work. The guys who make cheat engines, they have to put a lot of effort into it to actually convince the operating system to let them access these other memory regions here. And as said, administrator rights is the first thing that's required, because without that, you're completely out of luck. Of course, the administrator can do everything, but there is even things. I'm pretty sure there's processes even cheat engine will not be able to access. Because as said, cheat engine has to actively convince the operating system to actually let it access these memory areas. And there's memory areas that the operating system really does not want anybody else to peek into. Or there's processes that tell the operating system that under no circumstances they want to be peeked into. And cheat engine can't access these, no matter what it does. There's actually, on modern computer systems, there's very sophisticated memory protection mechanisms. Yes, and they are a pain in your rear six if, like me, you actually like going rogue on your memory and just full anarchy, all the memory is mine. Dear BKH, or Dr. BKH, or hi, a wonderful evening to you. Given you're in the same time zone than me, maybe if you're in the US, then it's lunchtime. Dinner. Wait, which is which? The thing in the middle of the day? No, it's lunch, right? Yeah. Hi. So, for the sake of demonstration purpose, because again, this is only pseudocode. This is nothing we can actually put into our compiler. Let's say our sum function is not a sum function, but it's some object. like we got the actor classes, the actor references when last time when we spawned our actors for the Game of Life implementation. We got those. I don't have it open right now. We always got those references to the spawned actor back, which were always pointers. So let's say this is some object, our red thing here, which just was in function. Now it's an object, and now we have, and for now this is only a class, right? And now we have some other piece of code here, and this other piece of code has actually it has a variable that is of type some object, and here comes the culprit asterisk, because this is going to be a pointer, and we just call this SO for some object, because my writing with the mouse is really so bad. So our other part of the code declared a variable that is the address in memory of an instantiated object that is of the class SomeObject, which is our class down here. Which is, again, exactly what we did the last few times when we got these actor references back, because they were new objects that were created somewhere in memory, and we got the address back. So now this code does something like SO. Oops. Do I have? Yes. New SomeObject. Jesus Christ, my handwriting with a mouse is really bad. Should have thought out that a bit better. So again, this variable SO of our code that's running around here, which color didn't we use yet? I think yellow is only barely visible. Let's use this dark red. So this is our variable SO. I hope the dark red is you can see that it's not the black. So let's say this is down here. This is where the compiler said, yeah, if you use the SO variable, this is the square in memory where I'm gonna be putting this. You manipulate the memory of the device emulator to trigger an error message. Yeah. Normal user space processes, you can do this. This works. So if we put something into SO, this is where the compiler said, okay, this is where I'm going to be putting this. And now we do this SO equals new SomeObject, which means we create a new instance of this thingy. And since this is the red one, let's still consider the red. I hope you can see my mouse. I'm not sure. I don't know. Is there a mouse visibility tool or something? So the red region up here, I marked in our memory grid. This is where our object is. And again, everything we put into a variable has to fit into a CPU register. So we can't put the whole object because this object is huge. I mean, look at it. This is 1, 2, 3, 4, 5, 6. This is 6 blocks of memory huge. And our CPU can only remember one of such a square in its registers. So instead of giving us this new, this new call here, instead of giving us the whole object, because the new, when we call this new, what it does is it looks for a free memory area and creates our object. And let's pretend it's this red area. This has just been created and filled with an instance of our object by this new function, this new call. So what this new call will return us now It's not the whole object, because again, this doesn't fit into a register. So it's returning us the address in memory where this object is. And in this case, it's at 2.7. So we get the 2.7 put into this memory square. This is what we're getting back when we're instantiating an object. And this is exactly what we got back when we spawned all those actors in the Game of Life implementation. Because what we got back was the address of where in memory all the information regarding this object, this actor, are put into. And if we want now to do something with this object, this is what I think I already mentioned this. And again, we're doing all of these things. We're trying them in code, and we're actually seeing how they work. And I also will demonstrate the shorthand. Because what we did on the actor was we called some functions on the actor because we want to do stuff with it. So what we can do, we have our SO. And I told you, if you have a pointer like this is a pointer, the address of something. If we want to access what is at this location, if we would print out the bare contents of SO now, if I would put a, not much space here, if I would put a print SO in here, the result, oh, whoa, what kind of arrow is that? The result would be 2.7. Because our variable, our pointer variable holds the 2.7. But the 2.7 is not the thing we want to be working with. We want to be working with what is stored at the location 2.7. Which is, if we again look, here's the 2 and here's the 7, which is exactly the beginning of our object we just created. And if we want to access what's stored at the location that we're holding in our variable, we put the asterisk again in front of our variable. There it is. If the pointer variable is a 1-byte value, your maximum map, yes, but this is only for visualization. This is not an exact mapping of modern day computers. This is only to visualize what I'm talking about. So we put the asterisk in front of the SO, and now we can access it. Like if I would do a print asterisk SO, that would actually have weird behavior because, well, the print can't really print objects. So yeah, that might be kind of weird. We can't immediately, you know, if we have objects and we want to call a function, a method on our object, we put the little the period there, and then, like, I don't know, call some function or something, some function we want to call, because that does very important stuff. For a few reasons, this doesn't work because the compiler then doesn't know, do I want to call this on the SO and the result is a pointer, or is the SO a pointer? So we have to make absolutely clear that the SO is our pointer and what's in there we want to access, so we just put brackets around it. Because without the brackets around it, it's not clear if the asterisk counts for the SO, or if the asterisk counts for the result of SO dot some function. Because that could be. You could have a structure or anything that you could immediately access, and you could call some method on it, and the method returns something, and that's a pointer, and you want to access what's on that location. So we have to make it absolutely clear to what the asterisk refers to, and it counts just for the SO. So we put the brackets around the asterisk SO, so the compiler knows, all right, okay, you just want to use this thing, which is a pointer variable, and then you want to access what's at the address stored in the SO. And then outside of the brackets, we have a reference to the location in memory where that thing is, so we can call our function on our just newly created object, which sits neatly here at address 27. So far, so unclear. Again, a simple analogy is imagine all of these squares. All of these squares are supposed to represent our memory, our gigabytes and gigabytes of memory. You can imagine these as drawers. You have a huge shelf, and your shelf is full of drawers, and each of these squares is one drawer. And there's pieces of paper in there. So if you open the drawer and you take the piece of paper out, you are reading what's in that memory location. So if you access, where is my mouse? Yeah. Like this, you have the integer variable x, and you just know, yeah, it's this drawer. You take this out, but the compiler takes care of this. You tell the compiler, dude, I want the piece of paper that's in the drawer I called X, and then the compiler takes care about fetching the right drawer and just giving you the sheet of paper that has the actual value, like in this example it was a 4 written onto it. But instead with the Y, and you don't know where it's coming from, you have no idea which drawer it is that your value is stored into, because the compiler takes care to just hand you the piece of paper that was inside of the drawer as a value. But if you have a pointer value like with the X, you actually know which drawer it is. You know it's the second from the left, and then the third from the down, the third down. So second to the left, third down, this is the drawer where something is in there. You have no idea what's in it. It's exactly the other way around. With this first one, this one, you know what's in there, but you have no idea in which drawer it is. With the other one, this one, you know in which drawer it is, but you have no idea what it is. So then you have to make this notation with the asterisk in front of your variable name, like down here, to actually tell the compiler, look, I know the drawer I want to access. This is the drawer I want to access. And now I want to actually open the drawer and take out the piece of paper that's in there, because the piece of paper is the value I want to look at. So the asterisk in front of a variable that's just holding which drawer it is basically open the drawer and look into it and look what's in there. Or you can also, if you assign a value, you can also put something in there. And this is basically what we're doing here. Then we say, okay, SO, we know in which drawer our object is. I put the asterisk in front of it because I want to actually open the drawer and access what's in there. And since in there is something with a lot of buttons that I can push that then do something, I want to push the button that's called sum function. Yes! I hope this was somewhat understandable and somewhat clear. If not, please let me know, either right now in the chat or later on down in the comments when you're watching this on YouTube, or at any time, either using this hashtag up there on Twitter or using one of those Twitter handles down there on Twitter. All of these ways will reach me, and I will see your question and I will try to answer it. So I think this is the time where finally We open our IDE, and all of these things that we just talked about in theory, like this is supposed to be our memory, and the red thing is our object, and this is that variable, and this is that variable. Let's actually try this, because there's one thing I haven't told you yet. There's one thing I did not mention during this explanation, which is the ampersand sign. We have talked about the asterisk a lot so far. We haven't talked about the ampersand sign yet. Because we will be doing this when we're actually in the engine and writing code. Not in the engine, in the editor, in the IDE, but we're running it in Unreal Engine just for convenience sake, because it's there. But we are not doing anything Unreal specific right now. Actually, we will be breaking a few Unreal rules. We will do a few examples that will definitely absolutely not work in Unreal, because I've mentioned this many times. For everything, we use specific Unreal types. With two exceptions, which is float and bool, we do not use the standard C or C++ primitive types. Always the Unreal specifics. We will break this rule a bit, but this is because we're not. While we're doing this, while we're compiling this and running this from inside Unreal, this is not Unreal code. This is just demonstration of how all the pointer stuff works. We're just doing this in Unreal because we will be using this later in Unreal, and we've used pointers a lot in Unreal so far. So that's basically the reason. Yeah, because we know how to access if we do know the draw, like in this y variable, if we do know the draw, we now know how to access what's in there. But I always said we have no idea what draw x is stored in. We just don't know that. We only, whatever we do, well, not whatever, but when we just access x, we always get the value that is stored in the draw, but we have no idea in which draw it's actually saved. And there's a way. There's a way, spoiler alert, because this is the ampersand sign. There's a way to actually get the draw of where the x is. Again, if I abbreviate this just with P for print, or let's do PR for print. If we just do a print x, this will give us, let's see, the 4. Because this is why I color coded this. This is this purplish blue, and here's our purplish blue square, and this has currently a 4 in it. So if we do print x, we get 4, because we always get the contents of the draw and we have no idea where it's coming from. But if we do something like print, and then here we have our x, this is supposed to be a bracket, and then we put the ampersand sign in front of our x. This means give me the address of this value. And this is the confusing thing, that just when you get told about it and just when you hear it, which is like super confusing, because it sounds like it's saying the same thing, but it totally isn't. This is the address of something. Well, actually, something like this. This is the address of something. This is something's address. Because with asterisk y, you only have the address, and then you can access the address to change the contents of what's stored in this draw or at this square in our memory. And with the ampersand, you have a value, but you access the knowledge of in which draw this value is stored. So if we do this print ampersand x, let's see, we have our 4. This is our x. maybe a different color. This is our X here. And let's see, this is at 2, 6. So print of X gives us the 4, which is the contents. And print ampersand X will actually give us 2, 6. Because 2, 6 is the number of our little square in our memory map where this 4 is actually stored in. So far, so good. Let's try this out. Oh yeah, this is the old stuff we did. So let's create, we are going down the convenience route again. We will be creating a little C++ component. Because then when we've put something in there, we'll create a blueprint actor where we'll just slap our component onto and then call our little demonstration function where we do all this neat and nifty pointer stuff. So this is pointer test component. And what's the date? The date is the 10th. So let's put this into 0910, which is the 9th month and its 10th day. Just so I have all the things, because I'm doing all these example thingies in one project, and just not to clutter one directory up and not know which file it actually is I want to use. Let's date code them, and let's see if this actually opens in the correct instance. Yeah, so we're creating an actor component, as you can see here. And again, those of you who were here the past few times know what happens with this. We can later on create a blueprint and blueprint actors. We can create a blueprint that's of the class actor. So we can use this as actor in the scene, and we can slap this actor component onto our actor and then just use it. We don't have to make a. We did this in the past. If you want to see an actor created completely in C++, we've done this. We've done this as an example. We've done this in the Game of Life implementation. So for the sake of getting this actually demonstrated, this is the right directory. Let's open them both, because I don't know, maybe we'll need them. First, let's clean them up again. Will enjoy banana cold. Yes, because I don't know, warm bananas. I once had something that something that was warm that had bananas. I don't know. Yeah, bananas are best served cold. That is absolutely right. And hi. Considering you might be in the same time zone than me, a wonderful evening, or a wonderful whatever it is in the time zone you're coming from. So this is private, but I don't know if you got any privates. Let's see. Yada 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 yada. Let's clean up this a bit, because this just clutters up stuff. It's the usual boilerplate things that we can clean up a bit. So let's have a little function that we call test. And let's also add this to the header. I will do this manually now because since we are going so low level at the moment and talking about pointers, I usually just use my IDE to create the declaration in the header. But again, since we're so low level at the moment, let me show you again for those who, I don't know, missed it or never understood it. Because every function that we are actually implementing in our .cpp file, we have to define in the .h file, in the header before. So let's do this. We have a simple test function, no parameters whatsoever. Let's make this public because we want to call this from the outside eventually. So this is void test, no parameters, semicolon, bam. That's it. That's the complete definition of this. But since we want to be calling this from the blueprint later on, because we have to have some way of actually calling our function, so we'll just call this from a blueprint. We of course put ufunction blueprint callable in front of it, like we've done many times before at this point in time. So now the red squiggly line becomes a greenish yellowish one, which is perfectly fine. It tells me something I don't want to do because it can be static, and no, it can't, because if we start using statics, we can just not use object-oriented programming at all, which right now we're not doing anyways. But well, yeah, you know, it's a matter of you know, of how to do stuff. All right, so where are we? Where shall we start? Let's actually do what we did here. Look at that. We had two variables. We had an x. Eventually, we had an y. We will call this p for pointer later on, anyways. But let's do this. Let's make let's actually make this a proper int32 because Unreal just like this. And let's call this a. And then we do nothing. Then this is perfectly fine for now. I'm going to be, for convenience sake, because those of you who've watched some of the previous sessions, you know that for my life, I just can't remember. Maybe eventually I will, but right now I just can't remember the syntax of the UE log macro that puts stuff into the log file. Because for those of you who've been there yesterday, well, we just dumped stuff into the log just to see what happens, just to see, yeah, this is that. We just put this into the log. Let's copy paste me some helper function that I just call print, and this we can actually just use the IDE to declare this. This does not have to be, whoops, I think I deleted, didn't cut it. This can actually be, you know what, just for the sake of doing it, let's have this blueprint callable as well. We don't need it, but well, now you know. No, just for the sake of doing it. So now I have a simple print function in my class that I can use to print something into the log. Again, I'm using warning to write something into the log so we can see our log entries, our texts we write out there a bit more easy, because the log is long. There's a lot of text in this log, and most of it is white. So if there's something yellow because it's a warning, it immediately stands out, so that we have an easier time of actually finding the things we're printing in the log. For now, we do them as a warning, so we have them in nice and yellow and can easily find them. And I don't always have to copy paste this and remember that. This is just a convenience function. I can just call print with my message to get something out of here. Yeah, still have to do some trickery. Anyways, so let's put something into A. The 4. The 4 was a good example. Let's put the 4 in there, and let me just copy paste this so I can keep copy pasting this because of remembered syntax. So what this basically does is writing something into the log. what happens if my line trace gets reflected by the glossy surface on the table? That is something you should have asked yesterday. So if you have your time machine ready, hop into it, go to yesterday, and ask this question. You will be surprised of the answer. Because the answer is really surprising. Well, actually it's not, but well, who knows? Maybe it's surprising, maybe it's not. So our value of A, and then we print the A. Don't be confused by this. For those of you who have some experience with C or C++ or similar languages, this is basically default placeholders for printf or sprintf, which is just a formatting thing. This 0x, because I'm printing these values in hexadecimal, because we will be coming to dealing with actual pointers, and they make a bit more sense if they're in hexadecimal, because just dumping them out as just decimal values, yeah, you could just smash your head onto the keyboard or on the number row. It kind of looks the same. So this 0x here, this will be printed out literally, because this only means this is kind of convention. If you have a number and there's a 0 and a lowercase x in front of it, then you know this is a hexadecimal number. If there's nothing in front of it, it's a normal decimal number, 8, 9, 10, 11. If there's a 0x in front of it, it's a hexadecimal number like 8, 9, A, B, C, F, 1, 0, 1, 1, and so forth. There's also things that it's binary or octal or whatever, but so this gets just literally printed out. The percent sign tells the printf function, like, okay, look, now comes a placeholder, because I want to print the contents of most likely a variable here. This is what the percent sign does. Let me stretch this out a bit. What the x does is the x defines what kind of value I want there. X is for a hexadecimal number, D is for a normal decimal number, S would be a string. I'm not sure if F is float. There's more. There's a huge list of placeholders. I want whatever value I give it here to be printed in hexadecimal notation. So there's the X. I want it to be formatted with, so it takes up 16 characters. So larger numbers and smaller numbers, they are right aligned. So it always pads with, by default, with leading spaces. Since I don't want spaces, I actually want a 0 there. This is this 0. This 0 says, okay, if you're padding this, then don't pad it with spaces. I'll pad it with zeros. So all the numbers look neat and tidy when we start printing several under them. Does it offer binary format too? Maybe B. That's a good question. That can or should be relatively easily asked with C printf. Yeah, let's just see if that yields something. Look at that. There's a link that I have. Yeah, look at that. So, binary you want. We have, let me enlarge this a bit. Oh, and by the way, Nico, a wonderful evening. Hi, nice for you to stop by. Sit back and enjoy. We are currently stumbling down a very, very deep rabbit hole, just as I promised. We are currently on our way down into the rabbit hole that is C and C++ pointers. Enjoy. So we have signed decimal integer. Unsigned, octal, hexadecimal, decimal floating point. Nope, no binary. If you actually want this in binary, you have to do something else. Maybe you have actually to write your own implementation. Oops. You would have to write your own implementation that actually converts any given number into strings of ones and zeros. But look at that. This will be this one will become important in a bit, because we have P for pointer address. Nice, huh? This will become very important because this is what we're dealing with. So just let this, let's keep this open. So there shouldn't be much of confusion. If we run this, we just should get value of A, which is A. Let's try this. Let's get this working at first until we then go further down. So we create us a little, where is it? Add new blueprint class. We make an actor and we call this BP pointer test actor. And we open it up. Oh, and one thing we should do, we should actually, yes, we should totally compile our code. Did I save? I think I did save. Let's hit the Borg cube and see if everything compiles. Yeah, we changed the header file. Changing header file always takes time. So this has compiled successfully, and we did not hear the nice compiler sounds it usually does, like this. Don't you love them? Don't you just love those sounds? Especially that one, because that one says, yeah, compilation successful. There's another one for compilation not successful. Also sounds nice, but this is usually not the one you actually want to hear. So we should find our pointer test component here, and we can just drag this out. And this shouldn't be too confusing for you guys anymore, because we've done this many times in the past. If you have no idea what I just did, rewatch the old episodes, because we haven't only done this, I've also explained them. Or maybe just ask if you really have no idea and you don't want to rewatch, like, I don't know, many hours of me rambling around, then just ask. So here's our test method. Here's our test method that we just wrote. We can just plug this in here and tidy this up a bit. So what this should do is, this should do nothing more than when our actor actually begins his life in the scene of the game, it calls the test function in our little class, in our little component. That for now should give us, if we don't forget to drag the pointer actually into the scene, we run it and look at this. How surprising. Here we got our log entry in nice yellow so we can actually find it. Value of A. Lots and lots of 0 and then a single 4. Because 4 is the value we put into it. And remember, I told it to pad it, to add padding characters. So the number's always 16 characters wide, because 64 bits. Oh, I said 8 bytes all the time. Yeah, it's actually 16. Or it's not. Maybe 16 is a bit too much. No, it's not, because pointers are quite large. Anyways. And this is why there's all the zeros, and here's our little 4, which is perfectly fine. This is actually what we expected. No, it's 8. Why did I do 16? because 32 bits is 4 bytes. So 64 bits should be 8 bytes. Yeah, 16 bits is 128. Yeah. Oh, this is already future proof. So we actually should be able to, oops, to make this. Why did I put 16 in there? Let's make this 8. Because, yeah, 32 is 4. Huh. Oh, this is, I don't know. I get confused sometimes. I don't know. How's it with you? Do you get confused sometimes? As you can see, I definitely get confused sometimes. Which is cool. Which is perfectly fine. Everything's okay. Did I compile it? Because... Oh yeah, this is the... We have to restart the editor thingy. No, there it is. Now it properly, see, now it properly formats this. Wait, this is 8. This is 16. Yeah, and this is 32. So this should be. I'm pretty sure the pointers for some reason will get bigger. You know what? Let's change this back to 16 because I think the pointers we're getting actually look bigger, but we can shrink this down anyways at any time. So remember the total confusion about the asterisk and the ampersand. I said if we want to know the drawer in which our piece of paper with our value on it is stored, we're going to use the ampersand. So let's do this. So let's just copy this. And let's get the value of ampersand A. Whoops. Let's do that. So up here, we're just printing the value that we put into A. Down here, we're printing out the address in memory where our value is actually stored. And you can see it already complains, cannot print value of type int that implies specifier P with format specifier X. Because this is a pointer. So this is what we've seen here. This is what we've seen here. Currently, I'm using X, which is an unsigned hexadecimal integer. So whatever value there is, it just writes them out as a hexadecimal value. Of course, pointers kind of are just hexadecimal values, but remember, C is very, very strict on its typing. You can't just do, well, you can't just put something of the one type into something of the other type. It's like trying to put a cube into a round cup. Well, of course, unless the cube is small enough, but consider they are the same. They have the same diameter. Doesn't fit. So we can cast this, but that's a confusion we'll be doing later on. We will start casting around. But for now, let's just put the P into there, and that should be perfectly fine. So let's compile this. And run this. Yeah, 1, 2, 3, 4, 5, 6, 7. For some reason, these values actually get bigger than 8 characters. So look at that. We got the value of A is still our 00004. This is really only 6 zeros in front of there. This is interesting. And the value of the ampersand A is this. Because this is the address in memory, somewhere in all of the many gigabytes of memory that my computer has. This is the address where this tiny little 4 is stored. Because this is the pointer to this. And now let's actually use something that uses the asterisk for the pointery stuff. Let's make another variable, b, but let's make this a pointer. And again, it doesn't matter if you write it like this, or like this, or like this, or even this. Of course, there's red squiggly lines under there because I'm redefining the same variable. That doesn't work. So ignore the red line for a moment. So it really doesn't matter your spacing. Where you put your spaces, how you write this. It doesn't matter. You can write it like this or this. You can put the asterisk just behind the type. You can put it just in front of the variable. You can put it in the middle of it and have it surrounded by space. Or you can put no spaces at all. It really doesn't matter. I personally prefer to write it like this because it's kind of the type. Because this, for me, this says, okay, up here, the A, this says I have an integer 32 value and I store this in the variable named A. This one tells me I have an integer 32 pointer. So I have something that points me, that is the address of an int32, and this I call B. So this is why I personally like to put the asterisk directly onto the type, because it's changing the type, because B is not an integer value. It's the address where an integer value is stored. But to make this a bit more consistent when we're actually accessing the B, I will write it like this, and you will see why. Because we said with ampersand A, we can get the address of where the value we store in A is stored. And I can put this into B. This is perfectly fine. This doesn't work. There's the, not sure if this is clearly visible. There's a red squiggly line below the equal sign. And it tells us I cannot assign type int32 asterisk pointer from a value of type int32. This is what when I just was scribbling around in Paint, where I said this doesn't work. We can't do it like this, because this is an integer value, and this is the memory address, the location where an integer value is saved. And technically those are different types, and this is the reason why I personally like it to write like this, because this sorry, because this changes the type. But again, you will in a few moments you will see why. For now, for consistency, I'm going to be writing it like this. So this is an integer value, and this is the address, the location somewhere in memory where an integer value is saved. So this is why I can't write this. I can't say B equals A. I can't put the value of A into B, because technically they are of different type. However, if I use the ampersand, I said with the ampersand I get the address of where the value of this variable is actually stored in memory. And since B is the address of a value in memory, this perfectly works. Because this is the address of my A, and I can write this into B. So let's print this out. If I say value of B is B, and we save and compile, and we run it, yeah, all right, and they match. Of course they match. Why shouldn't they? So here's still our little 4 that we stored there. And the address of where A is stored is this one. And the address that is stored in B, it's not the address of A or C or whatever. It's just a raw address stored in B. And this, of course, is the very same as the address of A, because we just assigned it to it. So now we got B, which has the address of A. And now let's do something. Let's do the access the address, what I said before. Because down here, remember, I said when we have a variable that's a pointer, like our B is a pointer. If we don't want to access the value of B, which is an address somewhere in memory, but we want to actually access the value that is stored on that memory, we also put the asterisk in front of our variable. This tells the compiler, look, compiler, you are about to get an address in memory. I don't really care about the actual address. I want the contents that is stored at this address. This is what this says. And so we can, I don't know, put a 7 in there. So, careful. At the location that's saved in B, we put a 7. And now we print the value of A. And now you can guess what happens. What is the result of this? Ning, 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 bidi, bidi, bidi. We save and compile. So again, we haven't touched A. We never touched A. We set A to 4, and this is it. Then we put the address of where A is stored into B. We printed everything out and everything's good. And then we accessed the address that's stored in B and we put something in there. We never ever touched A again. Let's see what happens. Compile. And run. And look at that. Our A contains 4. Then we have our 2 pointers. Of course, they're the same. But look at this. Down here, A. This is value of A. I'm not just printing A here. Let's again take a quick look at the actual code. I am actually printing A here. It's not just that in the string I say, okay, look, I tell you what's in A, but secretly I'm printing out B. We're actually printing out A there. But yet we get a 7 in there. A is 7, even though we haven't touched A. There has been, this has, I think this is something, we'll see what we get when we actually cast the address. The 7 has been put into the memory location of A. Exactly, this is it. The B9, I think it has something to do with, look here, if it says pointer address, and here it says B8, yada 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 yada. I think the B9 is a prefix. I might be looking this up for next week, because we are already closing in to the end of tonight's session. So I will look this up for next week, because here it says B8 and we got a B9. I think this is a prefix that actually tells us, look, this is a pointer. This is not just a random value. This is a memory location. And I will be looking up what B8 and B9, what those prefixes actually mean. So we might actually, this might be the reason why there's not 8 characters but 10, because it's putting this prefix in front of it. But let's try something else. Maybe that this changes the outcome a bit. Let's make another variable that we call p for pointer. And this is actually an int64, since our addresses are 64 bits in size. So this is a simple int64 variable. This is not a pointer. This is not nothing. This is just a simple int64, and this is a pointer. So let's try to get this into that. I already mentioned casting, which we can do. We can just do p. Classic C-style casting, because this is the only one I can remember, and thankfully my IDE can then translate this into C++ casting, is you have your value that's of a wrong type, like B. So this doesn't work for the very same reason this didn't work when I didn't put the ampersand there, because the types do not match. So what we can do is we can try a type cast to convince the compiler, look, take whatever this is and make it in as far as possible into a different type, which in this case, let's see, N64. So this is old school C, plain C typecasting. You just put into brackets the new type of what you want to have. This is the only type I'm good at remembering, because this is very easy. Thankfully, my IDE can translate this into C++ style casting, which uses a bit, which works a bit different, and we can do reinterpret cast. See, I just can't remember these weird words. It kind of works the same, just instead of the normal round brackets, it uses the pointy ones and puts the actual thing we want to cast into the round ones, and then puts a reinterpret cast in front of it. So what we have now is a 64-bit integer number, a plain number. It's not a pointer anymore, but it should represent the pointer. It should be of the same value, maybe minus the B9 prefix. So let's say value of p, and then this is not a pointer anymore. This is a hexadecimal value, and it's p. And since this is a very long p, we need to put the else in there so it knows this is an actually quite large animal. Let's see what's happening there. Let's stop this. Let's compile. I hope I saved. And let's hit play. And the result is actually the same. The result is actually very much the same, with the only difference being that this is lowercase and this is uppercase. But it still has the B9 prefix. And then possibly the actual memory location. Which I'm not sure if this is. I mean, the problem is, and this is where on modern computer systems this gets really confusing, because modern computer systems they don't actually address their memory like this. They don't address their memory actually like this. Modern computer systems they have virtual memory. The system, when you're on the operating system level, they don't use the actual physical memory location addresses in your memory bars that are plugged into your mainboard. The memory management in modern systems is quite complicated, and I'll be honest with you, I don't really know how it works. It's just weird. Because 4C something that sounds like a lot. Not sure if I have that much memory. Because this machine only has 16 gig. And this might be, even when we ignore the B9, the 4C something might be far beyond actual 16 gigabytes. But I'm not sure. I don't know. Wait, Windows has a calculator that can do stuff, right? Let's try. This is standard mode. Let's go to programmer mode. This is cool. Let's copy this. Let's paste this in here. Invalid input. Oh yeah, I need to go to hex. So this is the memory location without the B9 prefix, and in decimal this is like way too much. This is like 1.2 terabytes or something. Yeah, this is if this is bytes, then this is kilobyte. No, wait. These are bytes, so these are kilobytes. These are megabytes. These are gigabytes. 1.2 gig. Oh, that actually could work. That actually could be pretty correct. So it's stored somewhere in the first 1.2 gigabytes of my computer, which is funny because where's my task manager? Of the 16 gigabytes my computer has, 13.3 gigabytes are used. So that we actually got a memory location so far at the beginning. Well, memory fragmentation. Maybe there was something before and then I closed a program, so I freed up memory and the free memory has been recycled. But this actually could make sense. This could actually be, this could be right, 1.2 gig. This could make sense. So I just have to find out what the B9 prefix is. And I will note this down for next week. I will put this into the other notes. B8, B9 prefix on C++ pointers. Alrighty. So there you also got my ICQ number in case you're still using ICQ. I just leaked my ICQ number. Yeah. I'm not really using ICQ anymore these days. I did log on a while ago, not too long ago, and there was actually still one contact online. This was quite funny because we were talking ICQ and I was like, I still know my ICQ number. It's something 8176622 or something. And I actually, just for the fun of it, because you don't have to download and install it, you can use a web client. I just logged in and there was one contact online. This was quite funny. Maybe B9 is B8 plus 1. Yeah, maybe 42 is 41 plus 1. Which would result in a real address of 5.5 gig. Oh, that could be. I couldn't. Wait, 64. Yeah, no, but then if the one if the one would be actually had to be in front of that, and then we would have a 65-bit large pointer. It would be kind of, it could be page or something. I don't know. I will find this out. I will figure this out. I will figure out what the prefix with the pointers is. because 5.5 gig, that also sounds weird. Because with 64 gigs, you should be able to address way more than that. And the 8 and the 9 is already in way beyond the 64 bits. It's already in bits 65 to whatever 64 plus 8 is. Lakeside, a wonderful evening. Hi there. How are you? We're crawling down the rabbit hole, and it feels like we'll never be coming back because we've fallen down the rabbit hole of pointers. Maybe you know this. You know a lot of stuff. Look at this. Maybe you have an idea what this is. I got my addresses here, my pointers, right? And what? And he was long in the office and what? I was what? You were? Who was long in the office? I haven't been in the office at all today. Thursdays I always make home office because of this stream actually. Oh, you. Okay. So you have been long in the office. Yeah. Yeah, I hope everything's cool and you didn't have to do too much overtime. Yeah, on Thursday I actually make home office because of the stream actually. So I have a smooth transition from my working day into the stream, and I don't have to worry about getting at home at making leaving work at the right time early enough to be home early enough and then turn everything on and boot everything up, and which takes a huge amount of time, and just do home office and fire up the streaming PC when I do lunch or something. So when the stream starts at 6 p.m., all I need to do is to hit the start stream button and everything is cool. Only 3 hours over. Oh, you know, when you work on an interesting problem, I absolutely know this because this week I'm pretty much in this situation. I think I told this, I've mentioned this yesterday already. On Monday and on Tuesday, I really had a huge problem stopping to work and going home because I was making progress. It was so interesting and everything was nice. I just wanted to continue. On Wednesday, so yesterday, I had to stop working and go home because of the stream. If it wouldn't have been for the stream, I would have stayed rather long in the office again. Well, yeah, today I had home office. Also spend an hour going grocery shopping. Yeah, Lakeside, maybe you got an idea. Look at this, because these two lines, the ampersand A and the B, and also the P. That's actually a pointer. That is where our value, our A variable, is stored in memory. However, this part I'm just marked. This is a 64-bit value, and our CPUs are 64 bits in size. So this should be the memory address of wherever that thing is stored. And there's this B9 in front of it. And on the printf documentation, oh, whoa, what was that? That was totally wrong button. Wait a sec. On the printf documentation, where it says placeholder P on printf is pointer address, they have a B8 prefix. So and then they actually got only six numbers. So this is like totally weird. I have no idea what this means. This caused a bit of confusion today, but I'm determined to figure this out. Let's see if it's actually 8 bytes of address there. So this is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, The 4CB78358, that's a 64-bit thingy. And the B9 in front of it, I don't know. But we want to know. So I already know that it's down to figure this out, so I can tell you guys next week. But right now, I'm afraid I have to admit I have no idea. Maybe an LSIR thing. But if it would hint me how it's yeah, that could be. Well, I'll be spending my weekend Googling because I really want to know this. And once I know what these prefixes mean, and I think they mean something totally boring, but once I know what they mean, I'll let you know. Absolutely. I will let you know as soon as I figured out what these prefixes are. But I think it's something boring. It's something not super interesting, or I don't think it's something that'll make us go, wow. I think it's I don't know, something a bit more different. So yeah, what have we done? We just demonstrated how to use these pointers. Oh, by the way, let me show you my awesome paint skills that I promised you I will be doing. Look at this. Isn't this cool? Happy, or I'm dizzy to remember. Yeah, I will try to figure this out, to Google this out. I won't be figuring this out. I will only be finding out by torturing Google or stuff. So yeah, what we did is, and I think this will also bring this evening to its first conclusion. So we will definitely be continuing this next week. We got what have we got? We got our A variable here, and we just put something in there. The magic random number of the PlayStation. I think Dudler mentioned this before already. This is the random number used by the PS3 to secure its security stuff. Then we used the ampersand to get the address where our A value is stored. And we put this address in B because B is not an int32 value, but a pointer to an int32 value. Then we just tried the cast thing here just for trying out sake. And then we put something into the memory address that we have stored in B. And we never ever touched A again, but yet when we print the whole thing, when we get our output, we all of a sudden have a 7 in our A. And this is because we used the pointer to access the memory location where A was stored. We never touched A. But since we had the address or the drawer in our shelf where the piece of paper that has the value of A is put into, we could access this drawer, put something else on the sheet of paper, which of course has to change the value of A, because when we access A, it still looks at the same drawer. And so we still get the 7, even though we just used B to put it there. I hope this is somewhat clear. Again, please, I beg you, almost. If there's anything unclear with this, or if I maybe even caused more confusion than you already had, just let me know. Put it in the chat, put it in the comments, put it at the hashtag up there, put it at the Twitter handle down there, and I will see to answer your question. So let's do one last thing. Security by obscurity is never a good concept. Yeah, I think it was just laziness. It wasn't security by obscurity because they did use they did use the proper encryption algorithms. They had RSA and everything. Everything was perfectly fine. So they did it the right way. The problem was just that the random number generator that generated the seed for all the other encryption algorithms always returned the same goddamn number. This is loss of security by laziness. Or I don't know. I have no idea what went wrong there. Maybe it was an unintentional bug. Maybe someone, I don't know, forgot to put in a line in the source code, or I don't know. But something went horribly wrong, which eventually led to the PS3 losing its crown as unhackable system. But it was pretty good. Security on the PlayStation 3 was actually very, very good. And wouldn't have it been for this broken random number broken random number generator, I'm not sure it would have been hacked. Well, yeah, they did the memory injection thing, but there was still encryption all over the place. Let's do one more thing, because we have A. We have the address of A. And we have B, which is just an address. Let's check out the address of B, maybe. Let's see what this gives us. And then I actually want to try another thing. Let's do one more. Because here, this is by the way the reason why I wrote it up here, why I wrote it like this and not like I usually do. Because when we use this to actually access the memory location, we're doing it like this. We're putting the asterisk in front of the B again. So let's do this with reading. So here we have our value of A, and now let's see what the value of asterisk B is. Because what we're doing here is we're telling the compiler, look, you're about to get an address, and I want to access the memory at this location, and then it gets the B that holds the actual address, and we put a 7 in there. We of course can do this the reading way. We can tell the compiler, look, you're about to get an location in memory, an address, and I want to know the value that is stored at that location. I don't want to know, because if it do it like this, if I would leave the asterisk out, this is what we're doing up here. I get the address of B, or the address that is stored in B. Sorry, not the address of B. I get the address that is stored in our variable B. But I don't want the address that is stored in B. I want the content that is stored at the address that is stored in B. And you can already see why pointers are so confusing. It's just when you try to actually say what it means, mind blown. Because I want to try one more thing after this, and it might crash or it might not. So, but first, before we make it crash, and maybe just do save all in case it actually will crash later on, because there's one more thing I want to try, which is a bad thing, which is exactly the thing you're not supposed to do. But there's so many things you can do with pointers you're just not supposed to do. So, where is all our outputs? So, the stuff up here I think we covered, except for Wait a sec, need to push a button and need to get a different window up front. So the stuff up here we already covered, except for address of B. A is 4, of course, because that's the value we put in there. The address of where this value is stored is this one. And of course, so is what is stored in B, because we stored the address of A in B. So this is the very same. And now we got the address of B. Of course, that is different. And that's actually 16 bytes behind. And I hear you say, wait a second. From 85 to 60, that's not 16, that's 2. But this is hexadecimal. This is hexadecimal. So after the 8 comes the 9, comes the A, comes the B, up to the F. And only then comes the 6 zeros. So this is actually 16 bytes behind. Which is kind of like in our fancy scribbly art here. So this is the mouse pointer is very hard to see. The green one where the 32 is in, this is our A, and the other one is the purplish blue one with the 4 in it. This is our B. Only that each of these squares is 16 bytes in size. Wrong point is easy for program can let the program override itself. Yeah, self-modifying code, unfortunately something that doesn't work in modern computer systems anymore. Because with pointers, you can of course get the pointer of the, well, in C++, unfortunately, I tried it, but in C++, unfortunately, it doesn't work like this anymore. But in plain C, or even in assembler, you of course can get the memory location where the function that's currently running, or any other function. You can get the actual memory location of your program, where your program is at, and then you can write into these locations. And if you do it right, if you do this intentionally, then you can make something that's called self-modifying code. And it's called this because, well, this is basically what it is. The code that is running is overwriting parts of itself with different instructions, and may then jump to this other function that's memory we just have overwritten. And when this function then is executed, because this stuff is executed like it is in memory, not like it is on your disk, the things we just put in there are executed, which is very neat. You can have a lot of fun with this. A lot of things can go wrong with this. 1 second. Sore throat. You can have a lot of fun with this, but also a lot of things can go wrong with this. Unfortunately, for many reasons, this doesn't work on modern computer systems anymore. One of the main reasons why this doesn't work anymore is CPU cache. In old computer systems like the C64, or even the Amiga, but not all Amigas, only Amiga up to a certain CPU, because you have Amigas with newer CPUs like the 68000 030. I think it starts with the 030 actually, maybe even with the 020 already. Not exactly sure, need to look up. But on the old 68K, it still works. On the old 68,000 Motorola CPU, this still works. But around the 68K 020, 030, it stops working because these CPUs start introducing cache, CPU level cache. And then self-modifying code simply doesn't work anymore, because the CPU doesn't know that the memory location where it's currently executing its code have been modified. So it might have the instructions in the local cache, and then it's executing them directly from the cache and not from the memory, and so this doesn't work. Also, modern computer systems, like I already mentioned, there are security measures in place preventing this, because there's actually two ways. For one, you can't execute something from a memory location that is marked as data only, as not executable, because modern memory has a executable flag, and you can actually say this memory is just data. This is not executable code. This is just data. So if you try to execute something from there, like you're directly jumping into it, your program will crash, because the CPU already, this isn't even done by the operating system, the CPU will know this memory has been flagged as non-executable, and then the CPU will just refuse to execute this. And I'm not sure, but there might even be, it might even prevent you to write into memory that's marked as executable. So yeah, there's a lot of reasons why self-modifying code doesn't work these days, which is kind of sad, because you can do a lot of fancy things with self-modifying code. But again, there's even more things that can go wrong. So one very last thing I want to try tonight before we wrap this up and see each other again next week. I want to try to access some memory I'm not supposed to. It's not far away. This might work because the memory is so close by that it actually is part of my program. So I will be allowed to access it. And we will see. So again, just the last thing we did is we also got the arrows of B, which is a bit different than of course the one from A or the contents. But you can see it's very close by. It's only 16 bytes away. So you can clearly see that this variable and this variable, they are defined quite close together. Since they're even this might actually be on the stack. I'm not sure how C++ handles these things, because C++ with actual classes and class member functions and all these things, it works way more complicated than standard C, and I only know how these things work in standard C. I never caught up on how these things under the hood actually work in C++. Maybe I will one day. But this might actually be our stack. But I think this is going a bit too far anyways. So let's try one last thing and see if it crashes. We have our B, and B has a pointer to a 32-bit integer value. So let's add 1 onto the B pointer, which should give a very interesting result you might not expect. So you know what? To make this a bit more readable, we to find these parts there and not have to count. Let's put this separator line in there. So now let's see what's in B. Oh, let's see what's in B. Could make a song out of that. And then let's see what is there. But I comment this out for now, because this might crash, and I actually want to see the result of this. Because this might not be the result you're expecting. Because remember, we have our address of A, and we put this into B, and then I just add a single 1 onto it, and then we print the address that results. Let's try this. Compile and run. Oh yeah. Yeah, cool. Because this did result in the result I was expecting. I'm not sure what you expected. What did you expect? Unfortunately, we didn't have any fixed numbers, so I couldn't do a guessing game in the chat before trying. But look at this. In B, we have something 5.8. And remember, I added a 1 onto it. I keep the magnification open because we'll be going back there soon. I added 1. 1 I added to B. Okay? So, the content of B is actually something 5.8. Now I added 1 onto it, and the new content of B is something 5C. Whoops. What happened there? This is weird, isn't it? I'm not sure if you're just, I don't know, if you've already fallen asleep or if you're just like, what? So 5.8, let's look again. B is 5.8, 5.8 plus 1 is 5C. Now, how does that work? Well, the explanation is actually rather easy. And this will work. The program will actually not crash. It added 4. Yeah, but can you guess why? This is right. It added 4, but can you guess, or do you even know? Maybe you know, because I mean you're programming yourself a lot and in assembly, and I do think you know quite some C. Do you have an idea why it added 4? But I said I want to add 1. I'm gonna be waiting for the stream delay and then some typey, because there's a very simple reason for this. And for those of you who are expecting something that makes you go, what? The explanation is actually pretty simple. Maybe because of something 32 bit. Yeah, what? Maybe length of a value. Maybe. The length of what length? Length of a value is actually length of a value actually comes quite close. Of course, it has to do with 32 bits because 4 bytes are 32 bits. So of course, it has to do something with 32 bits. But length of a value is actually going into the right direction. But what value? And the answer is pretty easy. The compiler knows, and this is why there is so strict typing, because the compiler always needs to know. The compiler knows that in B, we have a pointer to an 32-bit integer. Well, actually, it doesn't matter to what. This can be a pointer to Schnitzelsalat for all it matters. It really doesn't matter. This really literally could be a Schnitzelsalat pointer. But the compiler knows that B is a pointer. And pointers are 64 bits. No. 32? No, wait, now I'm confused. Pointers are 64 bits. Well, it knows the size of the pointer. It's interesting that it's 4 bytes and 32 bits. That's actually quite interesting. Why this is a 32-bit pointer? Yay! Schnitzelsalat pointer, yo! Exactly, because Schnitzelsalat for the win. The thing is, the compiler knows the size of the pointer. The compiler knows there's a pointer in there. Oh, no, wait. It actually does have to do with the int32. Sorry. I take everything back. I take everything back and say the exact opposite. It does have to do with it being an int32. It cannot be Schnitzelsalat. Well, it can be Schnitzelsalat, but then maybe it would have been something, it would have not added 4 bytes, maybe it would have added, 42 bytes or something. The compiler knows that this is a pointer to a 32-bit integer. And the compiler also knows the size of an int32, well, which is surprisingly 32 bits. But if this would have been a float, this might actually be something else. We might actually try this, because this might have given us a different result. This might have given us a completely different result. So the compiler knows this is a pointer to a 32-bit integer. And the compiler knows a 32-bit integer is 4 bytes in size. So when I add 1 to a pointer, the compiler compiles this not with adding a literal 1, because the compiler doesn't see this 1 as a literal 1, as in our 5.8 would have become a 5.9. The compiler sees this as, I want to advance 1 value in memory of whatever type the pointer is. So it doesn't add a literal 1 to the actual hexadecimal number that is our pointer, but the compiler sees this as, I want 1 value further in memory. So I want the 32-bit number that comes after this one. And since the compiler knows that 32-bit numbers are 4 bytes in size, it actually adds those 4 bytes onto the pointer. So if we make this, the problem is we have to comment out a lot of stuff. How do we do this? Because if I would make this an int64, so let's comment out all the things that are not working anymore, which is basically almost all of them. Okay, you know what? Wait. I comment out all of this because we don't need this at the moment. I want to show you something else. So, okay, we have to make this working. So let's make an int64 as well. So we actually have something in B. We actually do have something valid in B, and we also do not need this anymore. So we can comment out this as well. So we still have our A, which now is a 64-bit integer value. And now let's keep this sign. And B is a pointer of a 64-bit integer value. And we put into B the address of our A like before. Everything's cool. So we should be okay with that because we just did this. And then I'm going to be printing out what's currently in our B. And then I will again be adding 1 onto it. And then I will again, once more, print this out. So before, the compiler knew that B points to values that are 4 bytes in size. So with every next value I want, the compiler actually adds 4 bytes, or added 4 bytes onto the actual pointer, because the compiler was like, okay, you don't want to literally add a 1 to your address, you want 1 value further. So I need to go 4 bytes further in memory to get the next value. Since we now have a 64-bit value that we're pointing to, the pointer should add 8 bytes onto it, because the compiler again knows B points to a value that is 8 bytes in size. So if you want the next value, we have to advance 8 bytes in actual memory to get to the next value. Let's try this. Let's try this. And run. Yeah, and that looks good. That looks pretty good actually. Look at that. Value of B before I add 1 is 58. The value of B after I added 1 is 60, and since these are hexadecimal values, this is actually 16. This is 16 more. No, it's 8 more. Sorry, I'm talking crap again. It's getting late. It's 8. It added 8. I think I said 16 a while back as well, which is wrong. I take this back. It added 8 onto it. Of course, it added 8, which makes total sense. Our 32-bit values, integers, they were 4 bytes, so it advanced 4 bytes. It added 8. It added 4 onto it. Since we now point to 64-bit values, it adds 8 bytes onto it, which is perfectly right. So let's give this one more try just for demonstration purpose. Make this something we'll definitely never ever be using in Unreal. Make this a character pointer. Oops, we already have the pointer there. We put the 4 in there, yada yada yada. This should work. Now it should actually only add 1. The 5.8 should become a 5.9 now, because characters are 1 byte in size. Let's try this, but maybe the size is different, but we'll see. We will see. Yeah, see? B is 5.8 again. And now I add 1 and I actually get a 5.9. Because now B is pointing to a value of type character. And a value of type character is exactly 1 byte in size. So now it's actually really adding 1. I hope this made sense. I hope this was understandable and didn't cause more confusion than it may be solved. Let's put all of this in just so we actually have some code, because there's one more thing I want to try. I want to try this line, but I assume it will work. It won't crash, because let's look at this. Compile. And run. Oh yeah. Ooh. Oh, I haven't changed the types up here. I didn't change them bit to int32. This is why it still adds 1. Oops. This is why it still adds 1. I forgot to change the types back. Yeah, this actually looks good. This looks good. So we got all of our old code back, just to have something, just to have some code in there and a few more variables. So B is 5.8. I add 1 onto it, so actually 4 bytes get added to the count to the pointer because of size of the value. So I get a 5C. What I'm gonna be trying now is to be accessing this pointer. And now again, it's up to you guys. What do you think? Will it work? Or will it crash? And can you even guess the result? The result will be interesting because it's again a 32-bit value. Because what we're going to do when we actually try this, because look at this, our A is stored at 5.8, and our B is stored at 6.0. So let me get this paint thing one more, and let me actually visualize you what's going to happen. We have, and now for the sake of this explanation, let's consider each of these squares in this thing is 1 byte. So we have this one. So, and in a different color, we got this one. We got 2 values that are 4 bytes in size because they are 32-bit values. The orange one is our A. Well, this looks crappy. Let me try this again. The orange one is our A. Yeah, that looks better. And the green one is our B. And B is a pointer. So let's mark this. This is the type. So we got in A, we put a 4 into A and eventually a 7. So the orange block, this orange 4 byte block, there's a 7 in there. So there's a lot of zeros and eventually a 7. And immediately following the 7 is the address of our 7. Because that's what we put into B. And when I added the 1 to my B, interestingly, it ended up being somewhere in the middle of these, because the address, let's go back to the address. Interestingly, it ended up completely in the middle. Yeah, okay, I got the memory locations wrong. I got the memory locations a bit wrong. Because the A is at 5.8 and the B is at 6.0. They are not completely adjacent. There's something in between. They're not completely adjacent. So I scribbled this wrong. They are not completely. This is wrong. This is there's something more. There's there's something in between. Anyways, what's going to be happening is this is our A, this is our B, and there's something in between, and we're actually going to access this one. And let's just see what happens when we do this. So I do think this will work. This won't crash. This will not crash, but what will be in there? It might be P. We never printed out the address of P. Let's do this. Let's also print out the address of our P, because that might actually be what we're getting. The problem is I don't know in which direction the compiler put our memory, our variables into memory. But let's find out. Let's find out. So what we're doing is we're having a totally valid address in B, which is the address of where our value of A is stored. We're adding 1. So we're adding 4 bytes, since it's a 4-byte value. And then we're trying to read out what's in there. I think it will work. It will not crash, because we have at 5.8, we have a variable of our own. At 6.0, we have a variable of our own. And 5C sits exactly in the middle between those two memory addresses. So that's a memory address that still belongs to our own program. And in your own memory, in the memory that actually belongs to your program, you can do whatever you want. Almost. So this should work. I don't think this will crash, but it will be very interesting what we get. Well, you can try this at home, but you shouldn't. Because now we're accessing random locations in memory. Did I forget to print, or didn't I compile? Did I forget to save? Because that last line is missing. There we have it. There we have it. So we have 5.8 in B. We add 1, which is 4 bytes because reasons. We get 4C. And when we then access a 32-bit integer, when we try to read a 32-bit integer from the 5C address, we get 2OE with lots of zeros. So this is interesting. I have no idea why, because I have no idea what's actually stored at this. Oh, look at this. P is actually at 6.8. P is actually at 6.8 even. It's way more further down. Yeah. 20E. This is what we're getting. So what we're basically doing is we are building ourselves a random memory address, and then we're accessing it, which is very, very dangerous. You shouldn't do this. This is only for demonstration purpose. You should never do this in an actual program, at least not on modern computers. If you still work on C64s or on Amigas or on old Ataris, yeah, you can do that. You can do that. It takes a while till bad things happen. But if you do this on modern systems, there's a good chance that you will rather quickly run into problems. If I would add quite a lot to this, which definitely is beyond the memory of my program, this might actually crash. Do you want to see it crash? Do you really want to see this crash? Should you make this crash? Let's add 10,000 to it. Come on, let's make this crash. Maybe we should actually run this with the debugger attached before it crashes. So before it does crash, because I'm very sure this will crash, let's do save all, let's compile. And I am very, very sure if the stream ends, you got a blue screen. Nah, the stream runs on a different PC. And also on modern systems, you're not crashing your whole system, you're only crashing the process that misbehaves. You're not crashing the whole system. And yeah, it crashed, of course. Let's restart this with the debugger attached. Here's the wonderful crash report. Let's go to debug game editor Win64 and run this with the debugger attached. This might take a while till it starts because it has to recompile everything in debug mode. And then we should be able to see the exact location where it crashed, and we should see an error code that will tell us nothing, most likely. But yeah, at least we're gonna be seeing more of the crash. Yeah, because this is, I guess we're getting an access violation, because whatever I'm doing here, this is way beyond the memory of my program. This is way beyond the memory that I got allocated and reserved for me. So it's memory where I'm not supposed to be looking at. But yet I'm doing it. So the operating system plays the big killjoy and tells me, access denied. Basically, it's an access denied. I think the actual error message, I think we will get an error message that's telling us something about access violation. So it should be compiled. Yeah, and it crashed. And here we go. Exception encounter access violation. Exactly. So let's see what's in B, because this is the nice thing with debuggers. You can actually peek into the variables, and even the debugger can't. So this is our B, and B now holds this value. Blah 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 blah. This is quite a lot more because we added so much. So this is the new address that's now stored in B, and even the debugger can't access it because this read memory from blah failed. 0 of 4 bytes. See, it did want to read 4 bytes because it knows it's an integer, and it's an 32-bit integer, but it can't because it's not allowed to access this memory. So let's see down here. This is the actual reason. This is what's happening. And it says, oh, you've encountered an exception at this address, which is very long. This looks like a 128-bit address, which is very confusing. Memory management in modern systems is very confusing. And here we go. Access violation reading from location. And this is the location that we added onto it. Then here's a bit more. Here's our values. Here's our B that doesn't work. There's the A with the 7. Here's our P. Yeah, in decimal pointers look weird. In decimal, I don't know, they look weird. They just don't work. So yeah, this is it. This was the first part of the deep dive into what makes C and C++ so special. Something almost no other language has in this way, and which can cause quite a lot of confusion. And this is pointers. And we even made a crash. There's way more funny and nice things. So next week we will be continuing on pointers. So next week we're actually having a pointers part 2, because there's quite some more stuff I want to show you and to talk to you about. And I also want to give you an example how these object references work. Because remember the example I stated so many times, when we spawned our actors in the Game of Life implementation, we got a reference to the actor back, which was an instantiated object, yada 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 yada. And I want to show you an example of this. We instantiate a new class, we create an object, and then we check out the address of the object, and we do, well, there's not much we can do with it, but we can at least look into our reference, our pointer variable. How does this look like? So that when we encounter things like, yeah, I don't have the Game of Life thingy open. But when we have all these references, like when we spawn an actor, we get an actor reference, or we have a component reference and things. so that you actually know when you write this. We had it here somewhere. I'm not sure we have. Yeah, here. When you write stuff like this, that you actually know what you're writing there, why you're writing this, and while you're writing this, you know what's gonna be in here, what it is that is in here, how it looks, what is in here, and what it does and how it works. I also will explain a bit more, once more, the shorthand with the arrow. I did this in this scribble here with the brackets around it. I will also pick up on this once more and explain a bit about this. Yeah, what else? We will create an object. We will have a bit more fun with pointers. We will be pointing around. We'll be creating objects, and we will... Oh yeah. We will take strings apart, basically with what I did here. We have a pointer. We add something to it, and we see. Only that in this in that case. We'll actually get sensible results because we are navigating in memory areas where we actually know where we are and where we know what's going to happen. Yeah. So, bit of overtime. So this is also the reason why I'll be calling this a day. We're going to be wrapping this up right now. If you have any questions, you still have a chance to put them in the chat. Tweet them at that hashtag, tweet them at those Twitter handles, or just comment below in the YouTube comments when you're looking the recording of this. This was Pointers Part 1. A little dive into the rabbit hole of how pointers work. I hope I could make it a bit clearer, especially with this little grid, that looks quite funny. I don't know. We should sell this as art. This might eventually become very, very valuable. So yeah, this is only the beginning. There's more to it, and we're going to be doing more, and maybe we'll do some castings, because there's one interesting thing we could do. We could change this pointer maybe to a float. Follow the white rabbit, yeah. One thing we're going to be doing next week, which will be very interesting, we'll be taking the address of our A, that's an int32 value, we'll be casting it to, let's say, a float, and then we'll be accessing this float pointer. And we'll see what will be the result of this. Oh boy. Yeah, I guess my throat wants to stop talking. So I think this is exactly what I'm going to do now. No, I just need this mouse. So yeah, let me find the right thing to click on. And thanks for joining. Thanks for watching. Like, share, and subscribe. Subscribe on YouTube. Subscribe on Twitch. On both platforms you can subscribe. Both subscriptions are awesome. Yeah. This is it. Next week, Pointers Part 2, because there's more and we're going to be looking at it. Have a nice day. See you around next week with more pointering. Bye-bye! And this didn't work. Why didn't this work? Why doesn't this work? I'm still there, right? You can still see me. Here we go.